Okay, now for what we have in the next part, where we have orthonormal sets tied in with orthogonal sets. Now we've had a lot of stuff to absorb from chapters 4 and what we have in chapter 5, and I know that there's a lot of stuff to intake, and it probably has a feel of trying to drink water out of a fire hose that is at full blast. But there is a bit of cohesion among the topics. And looking on with what we have here, and we have for orthogonal and orthonormal sets. Okay, now we have a set S of vectors in an inner product space V is orthogonal when every pair of vectors in S is orthogonal. If, in addition, each vector in the set is a unit vector, that is, where the norm is equal to 1, then the set is orthonormal. Okay, and for a set S that consists of vectors v of 1 to v sub n, okay, we have the following definitions below. Okay, and for an orthogonal set of vectors, okay, you're going to have that the dot product is equal to 0. And for orthonormal sets, okay, you had the dot product of the vectors equal to 0 and plus the norm of all the vectors involved will be equal to 1. And we have that orthogonal sets are linearly independent. And if S, again, is equal to a set of vectors, is an orthogonal set of non-zero vectors in an inner product space V, then the set S is linearly independent. And just examples of orthogonal sets. Okay, we have like a set B consisting of V of 1 and V of 2. And okay, so we have consisting of 1 and 7, negative 21 and 3. That's orthogonal since the dot product is equal to 0. And we say that B consisting of 3 and 4 as well as negative 4 and 3. Okay, that is also going to be an orthogonal set since the dot products will be also at 0. And also we have another set. If we have, say, 1, 7, 4 and negative 21, 3 and 0, we have yet another orthogonal set. Now, crossing over to what we have concerning orthonormal sets. Okay, now we have just examples here. Okay, we have B with v sub 1, v sub 2, and here we have the square root of 2 over 2, negative square root of 2 over 2, along with v sub 2 consisting of negative square root of 2 over 2, square root of 2 over 2. This is orthonormal since both v of 1 and v of 2, okay, when you combine them in terms of dot products, okay, the result is 0. And we also had the norm of what we have for v sub 1 and v sub 2, okay, that is also going to be at 0. Okay, so if I just apply the appropriate subscript here, so you got v sub 2, and for v sub 1, v sub 2 here, where we have the square root of 3 over 2, 0 and 1 half, and where we have v sub 2 is 1 half 0, negative square root of 3 over 2, that is orthonormal since we're going to have the dot product equal to 0, and all since we had the norms of both v sub 1 and v sub 2 to be equal to 1. Now, for what we have in the case of the Gram-Schmidt orthonormalization process, okay, now it says to begin with the basis for the inner product space, and it need not be orthogonal nor consist of unit vectors. And we're to convert the basis to an orthogonal basis and then normalize each vector in the orthogonal basis to form an orthonormal basis. And here is the theoretical aspect of what we have with what is referred to as the Gram-Schmidt orthonormalization process. And say if we have B to be a set of vectors and have that to be a basis for an inner product space V. Now for B prime, okay, these are going to be the resulting vectors, okay, where we're going to have, at least for this notation, will be what we have in the case of the formation of what is going to be regarded as an orthogonal basis. And if you have the orthogonal basis has to be rewritten in terms of the orthonormalization process. Okay, we're looking at taking the steps even further, and now looking at writing in terms of unit vector conversion. So if I take all of B prime, okay, taking the vectors and dividing by the norm of each vector. Okay, so you have like for instance, they have like maybe w sub 1 divided by its norm, and that would be forming u sub 1, and going through all the vectors that we have in the w sub n, you're going to have, in this case, in the cycle, you're going to have leading to the set b double prime, and this is going to be the orthonormal basis, okay, for this vector space. And just some examples here. Okay, say if you have the set B to consist of 1, 1, 0, 1, 2, 0, 0, 1, 2. And if you notice, okay, we don't have unit vectors throughout. And if I form both an orthogonal as well as an orthonormal basis, applying the Gram-Schmidt procedure. Okay, so you have for W sub 1, that's going to be V sub 1, which we have at 1, 1, 0. And W sub 2, that is going to be in the process, you have V sub 2 minus the dot product of V sub 2 W sub 1 divided by the dot product of W sub 1 with itself, and we take the ratio multiplied by W sub 1, which is originally V sub 1, and going through the proceeding, so we have W sub 2 at negative 1/2, 1/2, and 0. And for W sub 3, okay, where we had V sub 2, we're going to replace it V sub 3. And here we have V sub 3 minus, and you had the dot product of V sub 3 with W sub 1 all over W sub 1 times itself. And we have times W sub 1. And okay, where we have the equal sign, okay, the alternating error here, and that should be subtraction. Okay, so it's going to be minus V sub 3 dot W sub 2 all over the dot product of W sub 2 with itself, and you had that ratio times W sub 2. And for W sub 3, okay, going through the process, we end up with 0, 0, and 2. And that set B prime is going to be an orthogonal basis. Now, looking at converting W sub 1, W sub 2, and W sub 3 and writing in terms of unit vectors. So we got U sub 1, U sub 2, U sub 3 will be respectively W sub 1, W sub 2, W sub 3, all divided by their norms. Okay, so for U sub 1, we had the square root of 2 over 2, square root of 2 over 2, and 0. U sub 2, same proceeding, we have the negative square root of 2 over 2, square root of 2 over 2, and 0. And for U sub 3, we come out to 0, 0, and 1. And so this particular set that we have here is going to be what is regarded as an orthonormal basis. And also, for the vectors V sub 1 at 0, 1, 0 and V sub 2 at 1, 1, and 1, okay, we're looking at finding an orthonormal basis for this subspace. And going through the Gram-Schmidt orthonormalization process, you have W sub 1 is equal to V sub 1 is 0, 1, 0. And W sub 2, they have V sub 2 minus, okay, same proceeding, dot product between V sub 2 and W sub 1 all over the dot product of W sub 1 with itself, and we take that ratio multiplied by W sub 1, and for this outcome we have 1, 0, and 1. So you got 0, 1, 0, 1, 0, and 1, and those will produce what we're going to have. These will form an orthogonal basis. Now, in terms of forming the orthonormalized vectors, we have with U sub 1, so you have W sub 1 divided by its norm, and U sub 2 is going to be W sub 2 divided by the norm of W sub 2. And okay, so U sub 1 and W sub 1 are still the same since we have the norm of W sub 1 to be at 1. But for W sub 2, now we have the norm to be the square root of 2, so we're going to have 1, 0, 1 divided by the square root of 2. And rewriting, so we have square root of 2 over 2, 0, square root of 2 over 2. And we have, in this particular case, that is going to be our orthonormal basis. Okay, now let's say we are applying the Gram-Schmidt orthonormalization process for B, given that the set B consists of vectors V sub 1 to V sub 2, which we have to be at 1, 7 and negative 21, 3. And again, these were already orthogonal to each other, but we're going to go into those details in just a moment. Okay, so you have for W sub 1, that's equal to V sub 1, which is 1, 7. And W sub 2 is equal to V sub 2 minus the dot product of V sub 2 and W sub 1 all over the dot product between W sub 1 and itself, and taking the ratio and multiplying by W sub 1. And again, the dot product between V sub 2, which is at negative 21.3, and W sub 1, which was V sub 1 at 1.7. Again, the dot product is going to be 0 since we're going to have negative 21 times 1 is negative 21, 3 times 7 is 21, and negative 21 plus 21 is 0, so this whole ratio goes to 0. So W sub 2 turns out to be V sub 2, which is negative 21 and 3. So the set B prime, okay, that is equal to the set consisting of the vectors W sub 1, W sub 2, which is going to be 1, 7 and negative 21, 3 from the start, and that is going to be an orthogonal basis. And just closing out with the set notation. Okay, so that's going to be an orthogonal basis, and note, okay, the set B, okay, identical to B prime, that was already an orthogonal basis. But now V sub 1, V sub 2, or W sub 1 and W sub 2, okay, neither of these vectors will be unit vectors. And so looking at the unit vector conversions for both W sub 1 and W sub 2, now in W sub 1 we have a 1, 7. Now the norm is going to be the square root of the sum of the squares of 1 and 7. So you got 1 plus 49 is 50. So you got 1 over the square root of 50, which is going to be 1 over 5 times the square root of 2. And multiplying by W sub 1, and we have with our components, we have 1 over 5 square root of 2 and 7 all over 5 square root of 2. And for U sub 2, okay, so we got the norm of W sub 2. So you got the square of negative 21, which is 441, plus the square of 3, with the square of 3 at 9. 441 plus 9 comes out to 450. And in reduced radical terms, we have 15 times the square root of 2. So the reciprocal of that times what we have for W sub 2. And simplifying, so we come out to negative 7 over 5 times the square root of 2. Along with 1 over 5 times the square root of 2. And for what we have with B double prime, clustering together U sub 1 and U sub 2, okay, with these values, okay, that is going to be an orthonormal basis. Okay, now let's say that we have vectors that will not be orthogonal to each other, where we have the set B consisting of V sub 1 and V sub 2 with 1, 0 and 3, 2. And with the Gram-Schmidt process, so W sub 1 is equal to V sub 1, which is already at 1, 0. For W sub 2, we have V sub 2 minus, again, have V sub 2 dot W sub 1 all over W1 dot W sub 1. And again, with the ratio multiplying W sub 1. So here we have 3 and 2 minus, and here we're going to have the dot product at 3 and W sub 1 with itself. That's going to be 1. So you got what's going to be 3, 2 minus 3 times 1, 0. So that's going to convert to 3 minus 3 and 2 minus 0. So W sub 2 is equal to 0 and 2. And the set 1, 0, 0, 2, okay, that is going to form an orthogonal basis. And looking at putting this in an orthonormal basis terms, so if I convert the W sub 1 and W sub 2 into unit vectors, so I'm going to take 1, 0 and 0, 2 and divide by the norms of the respective amounts or vectors. And so we have for the norm of W sub 1, that is going to be at 1. And so U sub 1 and W sub 1 will be the same at 1, 0. Now for U sub 2, that's going to end up being 1/2 of W sub 2. So that's going to be 0 and 1. So B double prime is equal to 1 and 0, 0 and 1. That is going to be the resulting orthonormal basis. And let's say that if we have B to consist of two vectors with 3 components, where we have V sub 1 with 1, 3, 4, V sub 2 with 0, 5, and 5. So W sub 1 is equal to V sub 1, which is 1, 3, 4. And for W sub 2, we have V sub 2 going through the same procedure. So V sub 2, we have 0, 5, 5. Now for the dot product of V sub 2 and W sub 1, that is going to be 35. Dot product of W sub 1 with itself is going to be 26. So you got 35, 26 of W sub 1. W sub 1, again, we have it 1, 3, 4. and taking the difference, they have 0.55 minus, okay, and we have in the collection got 3526, 10526 and 70 13ths, and looking at the difference in this case. All right, so we're going to come out in this particular case. All right, so we're going to have in the mix, and I don't know why this was here, but taking what we have now, so we're going to have 0 minus 3526. 5 is at 130.26, and deducting 105.26, that'll be 25.26. And 5 we have at 65 13ths minus 70 13ths, and so that'll be negative 5 13ths. And now we have for the set B prime, so we have the W sub 1 and W sub 2. So we have 1, 3, 4, and then you have this set of fractions, and that's going to be our orthogonal basis. And looking at converting in terms of unit vectors. So W sub 1 divided by its norm. And again, the norm is going to be, again, the square root of the sum of the squares of 1, 3, and 4, which will be, in this case, the square root of 26. And taking 1 over the square root of 6 and multiplying W sub 1 will come out to these radical ratios. And for what we have for U sub 2, okay, so you have W sub 2 over the norm of W sub 2. And this one's kind of tricky. Now, for the norm of W sub 2, in simplified terms, we have the square root of 1950 over 26, and I could take the reciprocal of that and just multiply, okay, what I have for W sub 2 and reducing, okay, but leaving the radical in the denominator. So I have negative 7 over the square root of 78, 5 over the square root of 78, and negative 2 over the square root of 78. And for this set U sub 1 and U sub 2, okay, that is going to be the orthonormal basis in this third example. And we have with the remaining item, say we have B consisting of V sub 1, V sub 2, V sub 3, where we have respectively 1, 0, 0, 1, 1, 1, and 1, 1, negative 1. So for W sub 1, that's going to be V sub 1, which we have at 1, 0, 0. W sub 2, we have, again, through the same procedure, we have V sub 2 at 1, 1, 1. And we have minus the dot product ratio times W sub 1. And again, the dot product between V sub 2 and W sub 1. Okay, so that is going to be at 1. And the dot product of W sub 1 with itself, that is constrained to 1. So we're looking at 1, 1, 1 minus 1, 0, 0. And so that's going to be 0, 1, and 1. And for W sub 3, so we're going to have this time V sub 3 with 1, 1, and negative 1. And we have minus V sub 3 W sub 1 all over the dot product with W sub 1 and itself with the ratio times W sub 1. So for the dot product of V sub 3 and W sub 1, okay, that is going to be at 1. Again, the dot product of W sub 1 with itself is at 1. And W sub 1 we have at 1, 0, 0. And we have minus the dot product of V sub 3 W sub 2. And what's going to happen here is that for V sub 3, so you got 1 times 0, and you got plus 1 plus negative 1, and that's going to go to 0. So the dot product between V sub 3 and W sub 2, that is automatically at 0. And so we can say we have 1, 1, negative 1 minus 1, 0, 0, and that's going to come out to 0, 1, and negative 1. And so for this particular set here, okay, so W sub 1, W sub 2, W sub 3 with 1, 0, 0, 0, 1, 1, and 0, 1, negative 1 respectively, that is going to form an orthogonal basis. And for the orthonormal basis, okay, so if I take what I have with W sub 1, W sub 2, W sub 3, and divide by their respective norms. So we're going to have for W sub 1, okay, well, the norm of W sub 1 is going to be at 1, so U sub 1 and W sub 1 will be 1, 0, 0. Now the norm of W sub 2 is going to be, in this case, the square root of 2, and dividing W sub 2 by the square root of 2, and we have U sub 2 at 0, and we have the square root of 2 over 2, square root of 2 over 2, and for U sub 3, now again, W sub 3, we have a 0, 1, negative 1, and the norm of W sub 3 is the square root of 2, and dividing what I have for W sub 3 by the square root of 2, and just rewriting, I'm going to come out to 0, square root of 2 over 2, negative square root of 2 over 2. And for this set B double prime, okay, and so that's going to be u sub 1, u sub 2, and you're going to have, along with this, you have u sub 3. So you got u sub 1, u sub 2, u sub 3. And it's 1, 0, 0, 0, square root of 2 over 2, square root of 2 over 2. And then we have 0 square root of 2 over 2, and the negative square root of 2 over 2. And then just close this out. And so that is going to be the orthonormal basis involved.